Nadim Mohammed Khushu sir will also be joining me soon to hear the session. So we are going to start the session soon. So I'm going to read out the title of the paper and also the paper number. I request the audience present here to present the paper, the presenter. So the first paper from this session is paper ID number 92, and the title of the paper is an ultra-low energy efficient topological field effect transistor based on standing under perpendicular electric field induced topological phase transition. So I request the presenter of this work, Mr. Himan Roy, to present this topic.
There is a point of confusion. So, hello everyone and good afternoon. So, today I am now going to discuss about this topic, and the title of my presentation topic is an ultra-low energy efficient topological field effect transistor based on standing under perpendicular electric field induced topological phase transition. And here at the below these are the author's name, and the underlying name represents the speaker's name, and we are from Department of BUET. Here this basically represents the outline of the presentation that what I will be discussing about. At first, what the current issues that we are facing in our silicon-based technologies, and what kind of the methodology we can actually include this by overcoming such kind of the limitations. So we're discussing about this. So this actually explains our motivation of the work. Then the details of the proposed work, that means how we have found different kind of results or something like that. And finally, the important results and the comparison with the current roadmap, and how our system is actually efficient with respect to the current technology that will be actually saying here. And finally, the conclusion and the future work. So here now I'm starting. So you can see that in this graph, basically it represents that as the time is proceeding, so inevitably the demand of increasing the data that will also be increasing, and then you can see almost like exponential increase in the data. And at the year of the 2025, there will be the 181 zettabyte amount of data that will be generated. So it's one kind of 1 million petabyte, that is 1 zettabyte. So however, there you can see that while the data is actually increasing, then another way by which we can include our system efficient, that is increasing the device storage or increasing the device density. That means we have to scaling down the device. But at this point, when we are actually reducing the device, then there we can see such kind of a degradation of the short channel effect, the degradation of the subthreshold swing, different kind of the physics issues are basically offered. So we have to overcome it. And as our main topic is actually the FET, so we obviously have to control the electricity control in an efficient way. And in that case, the 2D materials actually gives us that platform where we can find the efficient electricity control. And now, while the 2D material actually comes in our mind, then at first graphene we can actually say that. But graphene is not actually suitable for us because it has no material. And even we may create the nanotube, but due to the edge roughness and even sensitivity with this barrier, it's not suitable for practical purposes. And even for the case of the germanium, silicon, and TMDs, these are not suitable because due to the interface engineering challenges and also the higher the impurity. So at this moment, the spin-orbit coupling, while we are going into the higher atomic number materials, then this important quantum mechanical effect actually manifests. That's the spin-orbit coupling effect, which gives the new kind of the quantum material property, which is known as the topological insulator. And this topological insulator, for the case of the 2D or the quantum insulator, this actually supports the current through its edge, and it's interiorly reacting like an insulator. So that's why the topological insulator name actually comes. And even on the presence of the impurity and even the edge roughness, the property, the transfer property will not be degraded, and that's why this is topological. And in that case, the best material from all of this perspective, the stacking actually suits all of the perspectives that can overcome this kind of issues. So stacking basically 2D topological insulator, which is the high spin-orbit coupling, and there you can see the structure of this stacking. And for the case, we have actually used the zigzag, not the armchair, because there are some also physics issues. So in that there you can see the direction basically represents the length direction, and this is actually the width direction, and how we have actually numbered the system. So we have actually used the 14 zigzag in our actually calculation. And not only that, from the top side there you can see it's actually the hexagonal structure, just like the graphene. But while we're seeing from the plane, then basically we can see that the atoms are actually separated by a particular height, that is the bottom height. And for the case we're studying, that is the 0.86 angstrom. So basically this is our proposed structure. It's actually a simple structure, so the dual gate phase. But at this moment the main thing is that we have actually used the channel material as a static. And from the top view there you can see the unit cells at the left and the right leads, and the silicon dioxide as the dielectric layer. So we have actually used such kind of the type Benz model and the non-infinite formalism for our transport equation and the transport calculation. And basically there you can see at the second portion, it actually represents the total time and Hamiltonian term. This is the first term, the real one. The second term basically comes from the spin-orbit coupling term. But this is the Halden's model. From this Halden's model, this gives the topological property. But the most important term is the third term. This is the standard sublet potential term. And then you can see that this L basically represents the Bartlett-Heimer static. And this that is the electric field that will be applied from the gate. And that's why there you can see the gate induced the phase transition will be occur. That means while we are applying the electric field, then this term will actually increasing or decreasing, and this will actually modulate the band gap of the system. And through this band gap variation, basically from the topological insulating state to the trivial insulating state, this switching will be occurred. So this step actually gives us another new switching mechanism, which replaces the conventional carrier inversion process that we are actually currently seeing in the FET. So now there you can see this basically represents the electronic properties. So this represents the band structure of this static, 4 is exactly static, and the on state. And just in the center here you can see the corresponding connection in the band, so K2 K prime and K2 K prime in the brilliant zone. And but there you can see this basically the signature of the topological insulating state. But there you can see the two overlapping versions, that is from the upspin and the downspin carriers. And for the case of the off state, that means while the electric field were increasing, that there you can see that there is no band. There is no connection. That is, they have completely created the band gap. So it will be acting like a trivial insulator. So this is for the case of the on state, and while we are increasing the electric field, this band gap will be increasing, and that will actually prohibit the propagation of the carriers, and this will be signifying our the off state. And now there you can see that for the case in the real space representation, this represents at the on state. And there you can see through the edge, the high local carrier density. This is as expected because for the case of the topological insulator, only the edge carries the carriers. But inside that bulk there you can see the vanishingly small local carrier density. So it actually prohibits the transport. So this is also the insulating property. But most important thing is that the carrier spin and direction of the propagation are correlated. And due to this correlation, the time universal symmetry are being protected. And that's why there you can say that the backscattering is prohibited. And that's why there you can see for the case of if this is the direction of the current flow, that is from this side to that side. This represents the case of the carrier transport, the speed will be the down speed. But if we change the direction, the down speed carriers will be flowing into that direction. So there you can see the speed and direction of the propagation, there is the correlation between that. And this gives the non-backscattering property of the topological insulator. And that's why the dissipation is transport at the room temperature. And basically it's nothing but at the energy domain, there you can see the local carrier density profile. At the topological insulating state, just at the previous slide there you can see, if we consider about this state, so at this energy state there you can see the high carrier density. So there you can see that just we have said, this insulating state represents the edge states. So there you can see as this energy represents the density of the states at that energy level. So this represents the high carrier density at the edge states. So these are the reflection from the position domain to the energy domain. But there you can see, obviously these are completed the band gap there you can see, so the zero density carriers. So finally this actually represents the result, and as you know that at the on state there is the linear relation because only the edge actually carries the current, and that's why there you can say that there is a constant quantum of the conductance, and that's why there you can see that the current and the bias voltage is linear relation, and into that case we have found that high on state current density which is much higher than the Broadband system value. And there you can see that this is the current channel current with respect to the gate voltage or the electric variation. And this represents the phase transition line. So basically below this line, this will be acting as a topological insulator. And this line represents at that point, we have not actually shown it into the band structure. But into that state point, there will be the simple touch between these two. That means direct semi-metal-like case. But at this moment, while there we can see we have entered into the domain, that due to the increase of the band, there we can say exponential decay will be the current. And that's why there you can see, roughly we have taken the 1.7 volt and the 20 nanoampere of the time will be offered.
And finally, the most important thing is that the channel will be acting like a capacitor. And as this is the 2D system, so there will be the finite density state inside the system. And for the case of the finite density state, due to the differential change in the gate voltage, we also know that there will be a differential change in the occupation of the density state. And this will give us the delta Q over delta V, that means the capacitance. But at that case, this is the quantum capacitance, not the classical. But into that case, what we have actually shown into our structure, that is actually the silicon dioxide layer. So these will also give us the classical capacitance. So they are basically the total capacitance will be the series combination between the classical and the quantum capacitance. And by that way, this actually gives us the variation of the quantum capacitance and the total capacitance. And while we find the total capacitance, from that we can easily find the gate capacitance. And this actually gives us the important transistor parameters. And these are the honest dependency, the gate capacitance, the delay time, and time for dissipation. We have actually found it. So from our proposed model, we can see that it actually gives much more better value than even the roadmap. And there we can see the 3-order improvement in the time for dissipation case. So it actually gives us a much better value, and it actually says the one can do proof of concept of room temperature, dissipation less, ultra low energy efficient topological phase, field effect transistor. And this is basically the reference from where we have taken the reference values. So this actually gives us that. So basically we have seen that this technique actually gives us an ideal candidate of the room temperature topological fit. That means dissipation less transport will be offered. And there will be the novel switching mechanism. That means we can, by applying the electric field, we can change the corresponding the band gap, and through this band gap variation, there we can see from the phase transition occurs from the topological state, that means the on state to the off state, the trivial insulating state. And also, if we include different kind of things, just like the Raspberry spin orbit coupling and some other different kind of quantum mechanical effect, we can actually harness much more better properties from that. So this is for our future applications. So that's all about my presentation. So thanks. So if you have any questions, then
Thank you for your presentation. The floor is now open for the audience for any questions.
What is the reason for such low power dissipation?
so basically, this is actually the topological insulator. So this is a new kind of material. It actually supports the current without dissipation through its edge. And there is some important quantum mechanical property, which is known as the time reversal symmetry. Breaking there will not be occurred. And that's why even on the presence of the impurity or the edge roughness, the transition will be occurred without dissipation. So that's why we can actually find such kind of the ultra low amount of the power dissipation, time for dissipation, the 3-order improvement. And this is the Fred-Newton per switching. That means why from the 1 to 0, we will be switching from 0 to 1. So per switching, even there we can say this kind of the Fred-Newton, this energy will be consumed here. Because this is the topological, so this is one kind of the manifestation of the importance of the novelty of the topological insulators. So that's it.
What is the voltage level?
Sorry, sir.
Supply voltage or something?
Oh, sir. Supply voltage, we have actually taken the 0.55 volt because from this roadmap, you can see that this actually represents the 34.7 nanometer node equation. At this case, the power supply voltage, we have taken the 0.55 volt. So from this roadmap, we have taken, actually, we have calculated all of this from the VDD, that means we have taken the 0.55 volt in our calculation. So this is actually the VIT. So I we have found from the RC current, and the VDD equal to 0.55 volt, and tau we have found this is from that. And tau is equals to actually RC. R we can actually easily found the bias voltage divided by current, and C basically we have found from that. This is actually the gate capacitance, and this is the series combination of the quantum capacitance and the classical capacitance. And basically this was our proposed structure. So these are basically the channel, and this represents this acts as the capacitor, but as it is the 2D, so there is the differential change of the occupation of the density of these states due to the differential change in the gate voltage. And that's why we have actually termed it as the quantum capacitance. And from this, through the NEGF or the different kind of system, we have found the carrier correlation function, and from that we have calculated this capacitance value, and we have actually used the value in that calculations.
Can you go back to the figure where you show the phase transition?
Okay. Yes.
Yeah. Is this voltage fixed for every time you are simulating the system?
But at this, so what kind of the voltage? This is actually the gate voltage.
Yeah. The voltage at which the phase transition occurs, is it fixed?
Yes.
So is there any way to tune the, if we are we defining at like the threshold voltage of turning on the FET?
Yes, at this moment this is just like the threshold voltage, you can see.
Okay, in this case, can you tune this threshold voltage by any means, by electrical means for this topological FET?
This can be possible, but at this moment we have to incorporate just like new kind of the materials. Even you can say if we actually replace the conventional silicon dioxide and if we replace it with the ferroelectric, then you can also actually change the threshold voltage value. So it's one kind of we have to improve new kind of the materials like the ferroelectric, something like that.
Thank you very much for your nice presentation and also for answering the questions. So a round of applause for our presenter. So at this point, we actually have with us our session chair, Professor Dr. Kaziri Mohammed Professor. So I'm ready to question. Thank you, sir, for joining us. So now we move on to the next presentation.